So unit 3 is called rational functions. In grade 11, do you remember doing rational expressions? It's the first unit. If you take it at Galt, at least, it's the first unit where you do a whole ton of factoring. And you've got like fractions of factors and stuff of rational expressions, and everybody's looking at me like I'm crazy. You don't remember this, or you do remember this? Kind of. Okay. You multiply them together and you add them together and you do all that work. So I have some review. It's not a ton, but it's something that you can work on if you have some free time, if you think you need to brush up on your factoring and your fraction work a little bit. So I will post, I haven't posted it yet, but I will post it, okay? And you can work on it. We don't really need to have it done until the second half of this unit, so it's not like due right away, but it's something that you can, chip away at if you have extra time. So we're doing rational functions. And the first half of the unit will be talking about their graphs, and the second half of the unit will be solving more equations and inequalities again, okay? And we're going to get into some pretty major sketching, like graphing, but sketching, right? So we're going to be graphing some pretty elaborate graphs. But before that, this first lesson is kind of a one-off, and it's on reciprocal functions. The reciprocal function is one that you did back in grade 11, and you did transformations on it, which are a big pain, so we're not doing that. Again, like everything else, we don't really do transformations. But we are going to talk about reciprocal functions, but again, we're going to talk about them in a very different way from how you did in grade 11. But it's the one that's really annoying because it's got a whole bunch of really small dots that are tight together, and trying to like transform them and move them around and stretch them is a real pain. So thankfully, we don't have to do any of that. Okay. So here we go. We're going to do 3 examples of this, and for each one of them, we are going to, the first function is going to be something we're familiar with, and we're going to graph it. And then we're going to use that graph to make sense of the second graph, which is going to be g, which notice is the reciprocal of f. So if f is x minus 2, g is 1 over x minus 2. That's what reciprocal means, right? What's the reciprocal of 2? 1 over 2, because it's like 2 over 1, so it becomes 1 over 2. So what's the reciprocal of 2 over 3? 3 over 2. Don't confuse this with negative reciprocal from grade 9. You don't change the sign. Okay, so we're going to graph each function. We're going to use f in order to graph g. And then we're going to state all this bunch of information, most of which we've talked about at the beginning of the course. So asymptotes, domain and range, intervals of increase and decrease are all things. We're going to do that just for g, not for both f and g. F is boring. G is the one we're interested in. And then this new thing, we haven't quite used this terminology before, positive and negative intervals. But that's just like when we're sketching polynomial inequalities, the polynomial function to solve. Where is it above the x-axis? Where is it below the x-axis? That's all that means. The positive interval is where the function is positive, above the x-axis. A negative interval is where the function is negative, the y's are negative, below the x-axis. Does that make sense? That's something you need to understand now. It'll be on a quiz or a test. State the positive and negative intervals of the following function or graph or whatever. Okay? So that's something that you do need to understand what that means. Okay, so we're going to start by graphing f. What is f? What kind of function? Linear function. So polynomial linear, straight line. That's an easy one to graph, right? It has a y-intercept of -2 and a slope of 1. And my rule of thumb, or my rule in my class, is if you have more than one function or relation or graph on a grid on the same axes, then you have to label them. Okay, so we're going to label this f. And now we're going to use f to understand what's happening with g and that idea of a reciprocal. There are two ways of doing this. The first one we're exploring. The second one I'm going to walk you through sort of a step-by-step method of how you should do it if you get a question like this on a quiz or a test, which you will. Okay? But there's sort of two ways you can do it. Okay? One way is we're just going to look at some points, and then the other way is by doing some kind of new thinking that you've not necessarily done before. And I think it's important thinking, and it's like number sense, and it's going to help in other areas of this course and stuff. But you could always, we're about to do it with just points, and you could get away with that. So, but you got to know one of the two methods, okay? So if f at x is x minus 2 and g is 1 over x minus 2, that means every point for f, g will be the reciprocal. So if I pick a point on f, like 2, what's the reciprocal of 2? No. Good, thank you. 1 over 2. So that's a half. So won't g be at a half? When f is 2, g is 1 over 2. Right? When f is 3, g is, whoops, 1 over 3. So that's smaller than 1 over 2. When g is 4, when f is 4, g is, thank you. And when f is 5, g is 1 over 5. So what are those points doing? What about when f is 10? 1 over 10. When f is 100, 1 over 100, that's pretty small. When f is a billion, 1 over a billion, that's really small. What's happening to those values for g? Very nice, good insight. They're getting smaller, but they're never going to be 0. Because if you take the reciprocal of a number, and these will always be numbers, f will always be numbers. It's going up. And those numbers are getting bigger and bigger. You'll hit a billion, you'll hit a trillion. 1 over a trillion. It's even smaller than 1 over a billion. F is getting big, 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 big. G is getting small, 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 small. Okay? What about at 1? What's the reciprocal of 1? 1. A graph and its reciprocal will always cross at 1 because the reciprocal of 1 is 1. That's an important idea. We're going to come back to that. How do I figure out where f goes from, or where g goes from there? Well, what if I pick values of f as they get smaller going that direction? So that's like about a half. What's the reciprocal of a half? 2. Whoops, did it again. What's the reciprocal of a third? So a third is getting closer to 0. 3, 4, 5. What happens when f is 0? What's the reciprocal of 0? Is it 0? It is not 0. Undefined. It's undefined. You can't divide by 0. 0 over 1 is 1 over 0, which is like dividing by 0, undefined. Remember that from grade 9? So it's undefined. And that makes sense because I can't take a number, 0, and flip it to get a number. So as this is getting smaller and smaller, closer and closer to 0, 1 over 100, g will be 100. 1 over 1,000, g will be 1,000. 1 over a billion, g will be a billion. As f is getting small, 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 g is getting big, 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 huge, 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 huge numbers, right? So f is doing something like this. Or sorry, g is doing something like this. Do you remember what that is? What's happening there? There's an asymptote there, right? There's an asymptote there. That's a more interesting way of thinking about this function than in grade 11 when you just plot points and stick them into that equation, isn't it? Relating it to the line that it's the reciprocal of. I think it's interesting. Okay, let's do it on the other half of the graph because we've only done one half of it. Here's f at -2. What's the reciprocal of -2? -1/2. -3 is -1/3. -4 is -1/4. -5, -1/5, and so on. What's the reciprocal of -1? Not 1. -1. Reciprocal of -1. You never change the sign. So they cross at -1 as well as crossing at 1. Then I could pick some points. -1/2 would be -2. -1/3 is getting closer to the x-axis, or closer to 2 would be 3, and then 4, and then 5, and so on. And this one goes like this. Something like that. Okay, then we always draw in and label our asymptotes. Use a ruler when you're drawing asymptotes. This is y equals 0. This is x equals 2. So listen carefully. We're going to do the properties of this one, all those properties that we're supposed to list, but then when we move on to the next one, I'm going to give you sort of a method, a step-by-step method that you could use to do these. But if you're ever stuck on anything, you always can come back to this idea that you're picking points on the function that you have and just taking their reciprocal. So at some point you're going to be doing work and you're going to be, wait a minute, is that right? Did I do it right? I'm not sure. Pick a number, flip it, and you'll know if you're in the right spot or not, right? Like you could just plot points kind of thing. Do you understand? Okay, so don't forget about this method. We'll still use a little bit of this, but not as much for the next two that we're going to do. We're going to use that thinking that as f gets very, 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 very large numbers, the reciprocal of a large number is a small number. And as f gets larger, its reciprocals get smaller. And as f gets smaller, meaning going towards, you almost picture yourself like on f sliding down towards the x-axis or something like that. You're sliding down towards 0. F is getting smaller, 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 smaller. G is going really, really, really big, really fast. Okay? That's that important. That's kind of different kind of thinking, but it's an important sort of connection to make or concept to grasp. The relationship between a number and its reciprocal. A big, big number in the denominator of a fraction means a small fraction. -1,000, -1,000,000, -1,000,000,000. The bigger the number in the denominator, the smaller the number overall, right? Any questions on this so far? Okay, so we have to state the asymptotes. So we do it like this. Vertical asymptote, we've already labeled it, but it's x equals 2. Horizontal asymptote, y equals 0. Domain, x is an element of the real numbers such that, anybody remember how to do this one? You did this in grade 11. Yeah.
X does not equal 0?
Not 0, though.
Or
2. X not equal to 2. It can be everything but 2. And you'll notice the domain always kind of matches with the asymptotes, because these functions will exist everywhere except for where there's an asymptote. Range. What's the range?
Y cannot equal 0.
Yep, y not equal 0. Okay. Intervals of decrease and increase. So I'm going to do something like this. I'm coming along. Am I increasing or decreasing? Decreasing. And I'm decreasing here as well, right? Because it's going to the left, it's approaching the asymptote from below. So going left, it's getting bigger, which means going right, it's getting smaller. Okay? So that is an interval of decrease. So when x is less than 2, and then it doesn't exist, and then we start up here, and it's still decreasing? Do you agree? So decreasing again here. X greater than 2. So when is it increasing? And you might say, well, does it increase at 2 because it goes from low to high? No, it doesn't exist at 2. When x is
less than positive infinity?
No. Less than positive infinity would include 2 and all of these numbers where it's decreasing. So nowhere. It's not, if it's decreasing everywhere that it exists, it's increasing nowhere. So there are no or none. Intervals of increase are none. There are no intervals of increase. Okay, finally, where is it positive? And this should be relatively easy, especially for this one. You still have to write it correctly, but you're literally just looking at where in the graph is it, and like you could just point. Well, it's positive there, and it's negative there. You know what I mean? But remember, positive means above the x-axis, so.
X greater than 2.
Yep, where x is greater than 2. So folks, that's this part over here is all positive. And it always will be positive because it's not going to cross that asymptote. And negative there. Right? So x less than 2. Is that good? Okay, before we move on to the next one, what we need to notice. These are the steps. Yep. Oh. Okay, I'm going to give you the steps. We're going to go over them a couple of times because we're going to do a couple of graphs. The hard thing about this is it's a one-off. So starting tomorrow with the next lesson, we start to do different things. And so then if you forget about this and you get to the quiz, and it will be on a quiz, and you kind of forget some of these important things, your graph will just be a disaster. Okay? This quiz, or this question on the quiz is almost always all or none kind of thing. People either get it and everything's good, or they really, really mess it up and nothing makes sense. So you got to remember these important points. First important point, and maybe the most important, the reciprocal will always cross the graph at +1 and -1. We're talking y values here, okay? They will always cross at +1 and -1. And when I mark this, the first thing I look for, does their graph cross at the 1s and -1s? I look for that. Yeah? Graph, the reciprocal will always cross the original function at 1 and -1. We're going to do this twice again as well, 2 more examples, so you'll hear it again. Okay? So the second important thing is when the original function has an X-intercept, that's when y is 0. When you take the reciprocal of that, you get undefined. That's a vertical asymptote. So you will always have vertical asymptotes through the x-intercepts. Okay? And then the third part of it could involve picking some points to kind of see what's going on with the graph. Or if it clicks for you, this idea of as this one gets bigger, this one gets smaller, and as this one gets smaller, the other one gets bigger, you use that to draw the rest of the graph. Okay, so let's see what that looks like for the second one. Some people struggle with this just because they can't draw the original graph, which is a bit of a problem. But I know that you haven't done a lot of this stuff in a while, so you might not remember all the little tricks to this. Sometimes the graph is given, like you'll notice the example on the back, the graph is given to you. But for this one, we have to graph it. So it's a quadratic. I'm going to graph it with transformations because in this case, that's easiest. Like we did all this work graphing in factored form, but I wouldn't graph this one in factored form. I would shift it down 4 and just draw a parabola. Okay. So let's do that. Vertex down 4. It's x squared. So every time I go over 1, I square it up 1. Over 2, square it up 4. Over 3, square it up 9. No stretch or compression or anything like that. You could also have factored this to get the x-intercepts, but that doesn't get us the vertex, so it wouldn't be as accurate a graph. Okay. Okay, now that we have the original function, here's where this process starts, so listen carefully. The first thing you want to do is mark your ones and negative ones. If you put a big point there, hopefully when you graph it, you'll draw through that point. You'll know that your graph is supposed to go through that point. So where are the ones? 1. People get confused about where the 1 is. I'm talking y equals 1. So there's 1 there and there's 1 there. They're not perfect points, but that's fine. Yes?
How do you know which x-intercept we use for the
What are you talking about?
Like, I kind of
Let's do these first. I don't know what you're talking about for x-intercept.
like when we did the y equals 1, how do we know which one, like which x value we put it at?
You put it where y is 1. It doesn't matter what the x value is. Like, I can't pick any x value other than that because that's where y is 1. This is where y is 1, right? Where those two lines meet. You know what I mean? And negative ones. So we've got 2 of each this time. That's step 1. Step 2 is draw in your asymptotes. Asymptotes go through the x-intercepts. I'm going to label them now so I don't forget later. X equals -2, x equals +2. Like those first 2 steps are going to get you off to the right track. If you don't do them, there's a very good chance your graph is going to be a disaster. Okay? So do that first. And then you either pick some points. I'm picking points on F, which is the blue one. So when F is 2, G will be a half. When F is 3, G will be a third. When F is 5, maybe I use that point because it's an actual point. F will be, let me get rid of, let me get rid of those. When F is 5, G will be 1/5. It's not a bad idea to even do one of those just to get an idea of where, like, so you have something to kind of draw towards. You know what I mean? And this is tricky because in here, it's really tight, but that's F values getting smaller, getting closer to 0. Okay? And as they're getting smaller, G is getting bigger. But what you, so if you understand that, then you just draw it. Yep.
So we can just like draw, we don't have to do like.
You don't have to do all the points. But you, maybe it's surprising, people do all kinds of wonky things with this. Like some people will draw a graph like this instead. It's like, okay, that's not following any of the stuff that we're talking about, but that's somebody who just knew the graph kind of looked like this and just randomly drew it. That's not a function because it's gone over top of itself. It's crossing the asymptotes, which is impossible. Like, there's all kinds of things wrong with that. So you can just draw it as long as you're doing it correctly and you understand. On the other side, same thing. F is getting really, really, really big, so G is going to get really, really, really small. In here, F is getting smaller, so G is getting bigger. And I know I'm approaching the asymptote. That's why it's there. So I know that I'm doing this. Or people do this, which isn't right. Whoops. So I want to get down to 1/5 there, so I'm going to really curve down. Okay? Now what about this bottom part? Well, I've got my -1, so that's good. And I know that this is going this way because F is getting smaller but negative, right? If the original function is positive, the reciprocal will be positive. All you're doing is flipping it. You're not changing the sign. If the original function is negative, which this one is here, the blue is negative, then the reciprocal will also be negative. So from here, blue is getting smaller and smaller and smaller, but negative. So this is getting bigger and bigger and bigger negative. What happens in this middle part?
And -1 is a third. -2.
Very good. So think about a couple of points. This is 1/3. Sorry, this is 3, -3. So this is -1/3. This is -3 again. So this is -1/3. And what's this? We know the vertex. It's -4. So this is going to be -1/4. Do we need all 3 of those points? Probably not, but I think you need that vertex point. And then just kind of connect them together. And it looks like that.
So they don't continue on being next to each other?
Yeah, of course. Because they can't go across each other. Then you wouldn't be a function. They're not two different things. It's one line. Going left to right, you're going up here and across and back down, right? So it's like, I know we're kind of thinking of it as two lines that are meeting, but it's one solid line. Any questions about that? Mark your ones and your -1s. Draw your vertical asymptotes through the X-intercepts. And then however you do the rest of it, how many points you need, or whether you're using points, or whether you are just using that concept of approaching asymptotes and that kind of thing, and bigger and smaller numbers, then you draw the rest of it. Okay, so let's do the details for this one. Vertical asymptotes.
X equals 2.
Oh.
X equals -2.
Good. Folks, I do not want these written like this. Asymptotes are, I'm sure some teachers allow this, but asymptotes are equations. So I prefer them to be written as separate equations. Okay? Horizontal asymptote. Oh, we haven't drawn the horizontal asymptote. So there is obviously a horizontal asymptote at 0. So I'm going to give you a little tip here. For these functions, not the ones that we're starting tomorrow, but for these functions, it's always just at 0. So if you can remember that, you could draw it in right away. Domain. Somebody want to give me the domain? Go ahead, David.
X is an element of the real numbers as long as it's not equal to 2 or -2.
Very nice. So you could also, like some people might do this, x less than -2, -2 less than x less than 2, x greater than 2. But the easier, oh dear. The easier way of writing that is x not equal -2 and x not equal, and you don't have to write those separately. So you could just even do a comma. Okay. Notice how that aligns with the asymptotes. There's a connection there for these kinds of graphs. Range. Does anybody want to try the range?
Y cannot equal 0.
That's true, but it's not the only thing it cannot equal. This one's a little bit different than the last one. What other y values does this function never reach?
Also, y is less than -4.
Not -4. -1/4, reciprocal of 4, right? Good. So y will be everything above the x-axis. So y is greater than 0, and y is less than or equal to -1/4, because it also equals 1/4. But it doesn't equal 0 because it's an asymptote. It's just approaching it. The last one side was approaching from above. The other side was approaching from below. So it was y not equal 0. These ones are a little bit different, so be careful of that. Decreasing and increasing. What's happening as I'm coming along here? Increasing. Am I going to be able to get rid of that without erasing the whole thing? Good. Okay, so that is when x is less than -2. Oh, increasing, sorry, I put that in the wrong spot. When x is less than -2. Okay, and then we jump, it doesn't exist at the asymptote, so we jump over it. And what's happening here? Yep.
Also increase?
Still increasing, but then there's a turning point, and what happens after the turning point? It's decreasing, so it's increasing. Hello. It's increasing between -2 and 0. And then it's decreasing between 0 and +2. Never include those points because they're asymptotes. It doesn't exist there. And what's it doing after the asymptote? It's decreasing, right? So when x is greater than 2. Okay, finally, the positive and negative intervals. Again, they're straightforward. It's positive there and it's negative over there. It doesn't have any x-intercept, so it's not crossing. So it's positive there and it's negative there, or it's positive there and negative in the middle part. Right? And then you just have to know how to write that. So positive when x is less than negative 2, and when x is greater than positive 2, and negative when it's between negative 2 and 2. Positive and negative intervals really don't have anything to do with increasing and decreasing. So like they don't line up or anything like that. You can be increasing in negative or you can be decreasing in positive, right? Like there's no relationship there. Any questions? All right, last one. So this one, the graph is given. Okay, so what do we start with? Go ahead.
The asymptotes?
You could. I said we start with the ones and negative ones. I'm going to do it that way, but it doesn't really matter what order you do it, obviously. So we'll do the ones and negative ones first. So there's a negative 1. There's a positive 1. There's another positive 1. There's a negative 1. There's a negative 1. There's a positive 1. Now we'll do the asymptotes. People do all kinds of weird things with the asymptotes. They do this. They put it through a turning point. Again, I guess they just didn't practice or they forgot or they're just not paying attention. I don't know. Asymptotes go through x-intercepts. This function is degree 3. It has 3 x-intercepts, so we're going to have 3 asymptotes. And if we wanted to draw in the horizontal asymptote now, you could. Let's see. I'm going to label them now before I forget. This is x equals negative 3. This is x equals negative 1, and x equals 2. Remember what I said. When a function is positive, its reciprocal is positive. When a function is negative, its reciprocal is negative. So if I'm starting from the left here, the function is negative, so its reciprocal also has to be negative. So this, from here, I'm approaching the asymptote from the left, going down. You could pick one point if you want. There's a nice point. Looks like negative 9. So I'm going to be at like negative 1/9 there, really close. Okay? Make sure you understand this. You can always fall back to just plotting some points, just figuring out some points, but okay, the function is positive here, so its reciprocal will also be positive. I'm going up. And again, coming down this way. And this time I've got 2 middle parts. Notice that you're given that point. That's going to be important. So the y value here is 2, so I'm at a half. And I've got my 1s, so I'm coming down. And this one, again, I've got my negative 1s, and I've got negative 4, so it's going to be negative 1/4. Something like that. Okay, and I haven't done my horizontal asymptote, so I'm going to add it in. Okay, now we do the properties. I'll let you do the asymptotes yourself because they're pretty easy. I want to get to the domain and range and the intervals of increase and decrease. So what is the domain? What x values does this graph go to? Or what x values does it not go to?
X is an element of the real number such that x equals not 3 with negative 3, negative 1, and 2.
Again, notice how it aligns with the asymptotes. How about the range? Anybody want to try the range? Think about what y values it can't be.
Isn't it just can't be 0?
Why?
Technically, the 2 on the, not the like 2 that curve, but the other 2 is like technically going.
Good observation. So a lot of people will, because of the last one kind of tricked us, and we don't want to be tricked by this one. They say, oh, well, y is going to be bigger than a half and smaller than negative 1/4. But actually, no, because it's true the blue graph doesn't get closer to 0 over there, but it does over here. So it's hitting every negative value up to 0 on this side. And people think of them as different graphs, but it's all one graph. And then same thing, it looks like it's not hitting some values here, but it hits them over there. Okay, so in this case, it is y not equal 0. Decrease. This is just for, like, when this comes up on a quiz. I'm just going to do this one when it comes up on a quiz. I just want to show you. So this part's decreasing. Right? So it's decreasing when x is less than negative 3. And it's still decreasing here to that point. And that point is negative 2.1. It's given to you. So in the case like this, you need that point so that you can define your intervals. So from negative 3 less than x less than negative 2.1. Then it's increasing, then it's increasing, then at 0.8 it starts decreasing again. So 0.8 less than x less than decreases to 2 because of the asymptote. And then after 2, it's decreasing again. so x greater than 2. And the increasing intervals are going to be all the rest. I think that's it. The positives are a bit easier because it's just between the intervals, between the asymptote, it's changing. So they're a bit easier to write because you don't have to use the point, but I wanted to make sure that I got that out there, okay? So you can do the rest. I'm going to do them quickly, if you can, or you can find them online if I don't get it done. Okay?